What?
Yeah. Hello everyone. So my name is Alex, and today I'll be talking about my project that I carried out during my PhD, which was the development of a novel rapid screening technique for radionuclides using test tubes. So basically, I'll be giving an introduction, just a general background of why there was a call for development of rapid screening techniques, talk a bit about the method, present some of my results, and then talk about some of the exciting future prospects that we have for test tubes moving forward, and then finally the conclusion. So the background, well, essentially, I think as some of us might already know, the UK is undergoing a large decommissioning project over 17 different nuclear facilities, and this constitutes a lot of legacy waste and site complexity challenges. This includes, because the sites across the UK aren't all the same, we've got stuff like heavy water reactors, helium-cooled reactors, fast breeder reactors, and stuff that brings a lot of different challenges. It's meant that the project is at the moment forecast to take over 100 years and cost over 120 billion pounds. I think that's already gone up since that last projection. So quite a large scale challenge, and the NDA understandably is trying to find ways to minimize both the financial aspect of the project as well as the time constraints. And this was outlined in a few documents released some time back, including the call for development of real-time measurements of ease of data manipulation, promotion of timely characterization and segregation of waste, and essentially calling for more developments of techniques that would be able to be carried out on-site rather than leaning heavily on off-site analysis as we currently do now. Testing technology looks to kind of address that and offer a rapid screening technique to facilitate off-site analysis. Essentially, it will be used as almost a check, on-site check to determine whether a specific radionuclide is present and whether that radionuclide is present in activities that are above or below a certain legislative threshold. For example, based on the EPR 2016, and this would essentially support waste sentencing, and the idea would also be that it would be able to complement off-site analysis. So off-site analysis would be reserved more for more complex samples and samples that would require a lot more complex radiochemical separations, and also give a faster turnaround time for samples that are on site and that can go towards waste sentencing. So to give an overview of the testing technology, essentially the target that we chose was strontium-90, simply because it's a major contaminant in nuclear facilities because of its high fission yield. It's a pure beta emitter, so therefore it's difficult to measure radionuclide. It has a relatively short half-life of 29 years, and it has bone seeker properties, which lends itself to also being a potential hazard for site workers. So it lent itself to quite a nice target radionuclide to develop the test for. And the extractant we selected was TP100 at the time, because it was just an ideal extractant to use on groundwater, and which was where we normally find strontium-90, and also it's quite mobile in that media, so TP100 worked quite well there, and its operability in neutral pH conditions meant that we didn't have to do any acid workup or anything like that, so kind of contributing towards that rapid screening aspect. So kind of a quick how-to guide. Essentially, we can break the testing technology down to 3 steps, essentially. So we have the preparation or manufacturing step, where we essentially bind the extractant onto the test stick using a sprayed adhesive. We use a commercially available spray adhesive, so nothing extravagant there, to be honest, on an inert support. So it was a readily available cellulose acetate inert support. We then allow it to set for about 24 to 48 hours just to make sure the extractant has an adhesive that's really set, so we don't get any extractant being released in solution, otherwise the test state essentially fails. After that, we expose the test stick to the sample itself for a designated amount of time, which is normally around 60 minutes, unless stated so. So normally in kinetic studies, we would change that, but for the most part, we left at 60 minutes. The test sticks would then be removed from the sample, washed with milky just to remove any solution that was on the extractant but not bound to the extractant. And then we would add a scintillant cocktail and then measure it by a liquid scintillation counting. So this is a general kind of overview of what I just spoke about, which can be kind of nicely summarizes each step. And one of the things that we try to really push forward with testing is the simplicity and ease of use, which means that it can be readily used by non-specialist personnel, and just makes it more of an attractive technique to be used both for on-site monitoring and maybe potentially down the line environmental monitoring. So this is a picture of the TK100 test sticks, and on the right and on the left we have the test stick inside a 5 ml cryogenic vial. On the background, if you've got a keen eye, you can see the post-it notes we use for the testing manufacturers. So obviously, we're at the cutting edge of technology here, but that will lean on to some of the stuff that we'll talk about. So today's some of the stuff that we'll be going over is determining mass loadings of the extractant, which is important for distribution coefficient calculations. Then talking briefly about testing response over strontium-90 activity range, uptake kinetics, and whether we can lower the sampling time, the impact of strontium concentration on testing performance. At what point do we start to notice testing performance start to diminish? Ionic interferences and their impact on testing performance, and finally, more of a conceptual topic is just the theoretical limits of detections with regards to count times. The target matrix here, like I said before, was groundwater, because the presence and mobility of strontium-90 in groundwater, and it presents a really nice foundation for testing work to be carried out, and then eventually moved on to more higher ionic strength solutions, potentially. So like I said, the first thing we looked at was mass loadings, and the first set of work that we did was essentially radio labeling the TK100 with strontium-90, manufacturing test sticks from that, and then setting some standards. This analysis showed that average test stick mass loadings was about 1.6 milligrams with a 0.4 milligram variance, essentially showing that there needs very, very little amount of TK100 to manufacture these test sticks, which is it's quite nice. It just lowers the manufacturing cost even further. But one of the things we noticed was that obviously we have that variance in test loadings, and the next step that we thought about doing moving forward was to actually individually weigh the test sticks both pre and post manufacture, just to kind of get a better idea of what that variance was. And so we did that over a series of 14 different experiments, just experiments that we did for looking at other stuff at the same time, and we found that the average test stick mass loading was actually higher, 3.8 milligrams versus the 1.6 that we saw in the previous data set, and the variance had doubled. And this essentially just comes down to human error. So making these test sticks myself presents, especially at the masses that we're working at, quite a lot of variance. And this can be better shown in this graph, where this just shows the individual test sticks that were manufactured over the 14 experiments, 96 test sticks in total. I've outlined some of the outliers where any number of factors could have affected this, whether I had coffee in the morning or anything could have affected that. But essentially what it calls for is that to look, in terms of future work, to look at introducing automation into testing manufacturing to try and lower these mass loading variations. But this is not by any means a bad thing. It's just something that needs to be accounted for when we're using the test sticks at the moment and what results they yield. The next thing to talk about, and essentially probably the most important thing when talking about test sticks, is the mechanism of uptake. So an important thing to remember here is that the test sticks don't function in a quantitative uptake mechanism. They're not looking to absorb all the strontium 90 that's in solution. They're just looking to form a proportional mechanism. So the more activity you have of strontium 90 in solution, the more you'll see on the test stick. What will that then mean is that, and that can be summarized in the second equation, is that we can essentially get a BT constant or proportionality constant, which we can use to convert the activity that we measure on the test stick to what the true activity of strontium 90 is on the aqueous space. So what we essentially did was we tested a range of strontium 90 activities and measured it on the test stick just to determine whether we had that proportional linearity. The hidden moral story behind this experiment was the fact that in order to improve the linearity and to what we can see now, we had to introduce agitation. We did that with automated rollers, which are what we believe does is essentially it disrupts equilibrium pathways and allows a lot better uptake over a wider activity range. So here we have uptake activities from 0.1 to just under 10 becquerels per gram. So kind of meeting that EPR 2016 guidelines of 1 becquerel. As you can see here, because we have that really nice linearity, it means that we could potentially predict quite well what the activity is on the aqueous space just by measuring what's on the test sticks. The next thing we also looked at, and again, it's arguably one of the most important things when discussing rapid screening techniques, is the uptake kinetics. So we did a kinetic study from 1 minute all the way to 48 hours, and what we found that was that between 50 to 60 minutes, we saw that the effective distribution coefficients for those time intervals were quite similar within an order of magnitude to what we saw at 24 and 48 hours, which for a rapid screening technique is really, really good. So what that essentially means is that we could potentially lower the sampling times or deployment times to between 40 to 60 minutes, which is only a good thing moving forward, and means that we can lower the turnaround times for test sticks. The next thing we start to look at as well was strontium loading capacity, or the effect of increasing stable strontium concentration in solution with regards to testing performance. And what we saw was that obviously as we increase the concentration of stable strontium, the performance of the test sticks started to diminish as well. But we see that happening more after the 1 ppm strontium, stable strontium onwards. And essentially what this also hopes to show is that even by constricting the uptake geometry of the extractant from 3D bulk phase to a 2D uptake when it's bound to the test stick, we're not actually lowering or affecting that much the uptake potential of the TQ100. It's still functioning quite close to what the product specification is supposed to be. And this can be better summarized in this graph where we calculated what the milligrams of strontium per gram of test stick extractant was. And as you can see, at around 100 ppm, we're starting to hit that product specification capacity for TQ100, which is about 8 milligrams per gram. And it really nicely shows that after 1 ppm stable strontium, we start seeing a noticeable reduction in testing performance, but in a realistic scenario, Southfield groundwater typically has around 1 ppm, sometimes less than that. So 100 ppm isn't really something that would be common to come across, but it's just a nice demonstration of how well the test sticks perform at a range of stable strontium concentrations. The next thing we looked at was ionic interferences. These ionic interferences were based off a National Nuclear Laboratory report that was done on the groundwater ionic composition. And what we found was that the performance of the testings actually didn't deviate that much between group 1 and group 2 ionic interferences, which was a really nice thing to see. There's a slight reduction in the performance of the testings with respiratory water. Not really entirely sure why that is, but that could be down to things such as, again, the testing manufacturer, the differences in extracted mass loadings, or anything like that. But that's something that we want to have a closer look at, see why that's happening, and understand it a bit better. But the take-home message here is that we're getting very minimal differences in testing performance between all 4 ionic interferences, and it shows that the testing actually perform well even in expected groundwater compositions. The next thing, and final thing really to show here, is a conceptual thing where we use the Curry equation and the proportionality constant from one of our studies to work out theoretical limit of detections between a ultra-low level LSE, like the Wallach quantiluses, versus a mobile liquid scintillation counter like Beta Scout, and just demonstrate really how potentially we could reduce the count times of the testings. For the ultra low level LSE instruments, we used an average background of about 7 CPM, whilst for the mobile LSE we used around 30 CPM. And what we found out was that for ultra low level, we could, within 5 minutes, we're able to reach an LFD target of 0.1 becquerel. So we used 0.1 becquerel because it's just 10 times less than what the EPR guideline limits are. So it's kind of a safe bet. Whilst for mobile liquid scintillation counter, that was around 5 to 10 minutes. Obviously, it can vary between different tabletop scintillation counters, but this is more of just a demonstration, and basically, potentially we can just lower the turnaround time for testings to potentially within an hour, which is really impressive. What is arguably the most exciting part of all this is the fact that we have a lot of choices of what we can do with testings moving forward. And one of the first things that we potentially look at is, just like I said before earlier in this talk, is that we can introduce automation into the testing manufacturer, lower those mass loading variances from testing to testing. We've discussed about using stuff like 3D printing, electroplating, and even, I think as Ord shown in her slides, even using some membrane filter where we could, because quite controlled loadings, we could use that as well. Another step that we're looking at following is using scintillant embedded extractants to minimize the use of scintillant cocktails for direct measurement, and that would only speed up the analysis process. And finally, just looking at what other extractants for other radionuclides of decommissioning interest. One of the ideas that we're kind of playing around with is actually trying to target yttrium-90 instead of strontium-90 using stuff like a DJ resin, and then using potentially some form of Cherenkov counting instead of adding a scintillant cocktail, and removing the need for a scintillant cocktail altogether. And one of the end games really is starting to work on multi-extractant systems. So once we start building profiles for testings for different radionuclides, we could essentially have a testing with different extractant strips and use a solid phase scintillator counter and essentially screen for different radionuclides simultaneously, further reducing the turnaround time for analysis and to help waste sentencing even further. So in conclusion, like I said earlier, TestIT looks to address the calls from the NDA for development of rapid screening techniques to complement off-site lab analysis and allow for offsite analysis to be reserved for more complex and difficult to measure samples. Low mass loading is required for testings to function, and initial results indicate that near maximum uptake efficiency in supposed to be 40 to 60 minutes. Apologies. And yeah, starting the testing yields more efficient proportional uptake over a range of activity. And that essentially we demonstrated the potential to lower count times as well, 5 to 10 minutes, which would result in analysis being carried out within the hour, which would be ideal. And finally, there's a large number of possibilities in future work, which would be quite exciting testings, and Triscam play a huge role into that with the extractants that they have available. And yeah, so I know I sped through this, so apologies. But yeah, finally, I'd like to thank the NPL for funding this PhD project. My PhD supervisors, Bill Warwick and Ian Crowders, industrial supervisor Steve Walters, and the GAU Radio Analytical for allowing me to carry out most of my work there and for helping me with the technical aspects of this project. And yeah, and also a big thank you to Triscam for making these extractants available for us to use for the testings, and look forward to working with more new and exciting materials. But yeah, if you have any questions, please feel free to ask. Thank you.
Thank you very much. Very interesting topic. And we just checked, so I think later on we will look into ticket 25.
Yeah.
The demolition that looks good. I'd like to see ticket 105 tonight.
Yeah.
It might be quite nice. There's lots of possibilities.
Yeah, and I think Ford's presentation actually showed quite a few extractants that would be quite interesting to implement. So yeah, like I said, like I just said, I think there's a lot of exciting potential for what we can do moving forward with testings.
Standards including the scintillating.
Yeah.
Directly, that's interesting.
Yeah.
And so you'll see later we do like TLC paper. The process is very similar to membranes.
Yeah.
So you go to different types of impregnation process that tends to be quite homogeneous. So and then really easy to upscale. So that might be another step in that direction.
For sure.
Interesting to test.
Yeah. Towards the end of the PhD, we had a few opportunities to work with some of the materials that Triscam sent over, but unfortunately ran out of time, which is quite unfortunate. But yeah, those materials would be really, really interesting. And I think if we can lower that mass variation on the loadings, we can actually improve a lot the performance. I think that could be quite an easy win.
I think that is going to happen.
Yeah.
So you're seeing that kind of application that we're doing for the other materials that tends to be very homogeneous.
Yeah.
That looks pretty good. Depending on the TLC paper, you see it's TLC. So if you put in water, you're doing like a TLC with the water, so that might change your kinetics here a little bit. So we will see how this is.
Definitely something worth looking at.
Oh, very, very exciting. So it's a lot of things we tested. So you'll be very busy, man.
Yeah. Sounds like it.
Okay. Then thank you. Are there any questions? Sorry. Are there any questions? We've already started chatting.
Yeah, actually, I do have a question. This is Aude speaking.
Yeah.
So this testing, you were talking about the LOD. So, but to be sure that you always, so I guess depending on the amount of material on the testing, it means that sometimes, I mean, will you do, or is there because finally, to be sure that you detect something, you increase you might increase the time of counting, right? So to be sure, do you have a limit to see, because this is a screening one. So what is the limit of the screening actually?
So the limit of the screening would be around 1 becquerel, which is from the EPR 2016 guidelines, which is I think the boundary towards very low level waste, which testing is what testers look to essentially help out with, is just distinguish whether samples are out of scope or LW. So we picked to do a 0.1 becquerel as an LOD just to be safe. So because if we did, for instance, at 1 becquerel, then we couldn't be 100% sure whether a sample was above or below that if we're working an LOD very close to what we're looking for. So that's why we did an order of magnitude less, was that we can then be sure that we could see for sure whether a sample was above or below that limit.
Okay, thank you. That's a very nice technology, I'd say.
Yeah.
It's going to save a lot. It's going to save a lot of time, actually.
Yeah, that's the dream.
So, yeah.
Yeah, thank you.
Okay, so no other questions, then thank you again.